So redox reactions, when they're basic, you do them just like you would do an acid one. You take care of the fact that it's basic at the very, very end. So we're going to start this one. Now this one's a little different than what we're used to because there's like 3 reactants over here, and there's only one product. So let's talk about this one. So the first thing you always want to do is split the things into half reactions. So you go, okay, well, oops. I see that there's silver and cyanide over here, and I would have to have both of them in order to correctly balance this. This thing is called a complex ion. You don't need to know that, but it's complex because it's complicated, okay? Right, so like let's assign oxidation states. So cyanide is -1, right? And there's 2 of them. So that's a total of -2. Well, the total charge right here is -1. So silver's +1. Well, over here, silver's 0. Okay. So the silver is losing electrons. So this is my oxidation half reaction. Now notice the cyanide is -1 in both sides, so the cyanide isn't actually participating in the redox. It's just the silver. It loses an electron to become +1, which also makes it the reducing agent. Okay, and again, I included both of these guys because in order to balance this guy over here, I'd have to have both present. Otherwise, there's no way to balance it. Okay, so the other half reaction, just the other reactant was O2. And then it went to like nothing. So you go, well, what do I do if there's no oxygens on the product side? Well, you do the same thing you always do to handle oxygens. What do we handle oxygens with? We do it by incorporating water. So we're just going to add ourselves 2 H2Os over here to get my 2 oxygens. So let's look at oxidation states. Elements, pure elements, are 0. Hydrogen is +1, but oxygen, so we're focused on the oxygen. Oxygen is -2. So this is going from 0 down to -2. It's being reduced. It's reduction going down to -2 because it's gaining electrons. So this is my reduction half reaction, which also makes O2 my oxidizing agent. Do you have any questions on how to do that? Now, you didn't have to do this right off the bat. I'll show you how else you can tell who's being oxidized and reduced in a minute when we start balancing the half reactions. It's really going to be where the location of electrons are. If electrons are coming out as a product of a reaction, that means the substance over here is losing them. So it's an oxidation reaction. If electrons are going in as a reactant on the product side, this thing on the reactant side is gaining or taking in electrons. So that's a reduction half reaction. So you'll see by the location of the electrons also another way to identify whether what substance is being reduced and oxidized. So now that we have our half reactions, we're going to balance. So the first thing you always do is you balance all elements other than oxygens and hydrogens. So that would be like your silvers and your carbons and your nitrogens. So look I see 2 cyanides over here, so I'm going to put a 2 right here. 1 silver, 1 silver. Okay, so we're good there. Next thing you balance are oxygens. I don't have oxygens. The next thing you balance are hydrogens. I don't have hydrogens. The next thing you balance is charge. So the charge over here is -1, and the charge over here is -2, because 2 negatives. So I need 1 extra electron over here. -1 and -1 adds up to -2. Okay? All right, so that half reaction's done. The next half reaction. So I have, I already balanced my oxygens. I just did that to even be able to write the half reaction. So I have 4 hydrogens over here. So I will put 4 hydrogens over here. Okay, so all elements are balanced. So now I need to balance charge. It is no charge over here. So I needed to have no charge over here. And right now it's +4. So I need to add 4 electrons to this side. So +4 minus 4 is 0. This is 0. Everything's 0 for this one. Okay, so now that both of my half reactions are balanced, I force the electrons to match. I do whatever it takes. I multiply the equations by whatever it takes to force the electrons to match. So that would require me to just do this top one and multiply it by 4. So I'm going to rewrite it down here. So that would leave me with 4 silvers plus 8 cyanides. Oops, sorry. Makes 4 silver cyanide ion and 4 electrons. Now you can either, whatever you do, you want to get rid of this. You don't want to look at this top one anymore because it might mess you up. So I'm just going to erase it. Okay. And now we start reducing. Everything on opposite sides needs to cancel or subtract if they don't perfectly cancel, and everything on the same side gets added together. So 4 electrons on the left, 4 electrons on the right. They perfectly cancel. Is there anything else that cancels? Yes or no? No, there's nothing else. It's the same. So if this were done in an acidic environment, we would be finished. You would just write out everything you have. But because we are in a basic environment, we are not allowed to have hydrogen ions float around. So we will take care of this at the very end, which is where we are right now. So you go, okay, if there's 4 hydrogen ions, I need to add that same amount of hydroxide ions to get rid of the hydrogen ions. Okay, and just like in math, if I add 4 hydroxide ions to the reactants, I better add 4 hydroxide ions to the products, otherwise things won't balance. You don't get to just do it to one side and not to the other. If this would have been 10 hydrogen ions, you would have added 10 hydroxide ions. If this was 50 hydrogen ions, you would add 50 hydroxide ions, and again, to both sides. Now, this is the part that confuses kids. You got to remember that H plus and OH minus make HOH. And HOH is water, H2O, H2O. So if there's 4 of these and 4 of these, you get 4 of these. So I'm going to rewrite this as 4 waters because that's what it is. Now, because this happens, I have to go back and check my waters, meaning I need to re-reduce them. I have 2 on the left here and 4 on the right. So I'll lose all 2 of these. And 4 minus 2 is 2. So there's 2 left over right here. Now I'm finished. So it's a little bit of extra work to do a base. So now you just write out everything that's left. I have 4 silvers. I have 2 waters. I have an O2 right here. I have 8 cyanides. All of that is on the reactant side of the reaction arrow. And then I have 4 of this complex ion. Plus 4 hydroxides. So let's look. Let's see if everything is balanced. So 4 silvers on the left, 4 silvers on the right. 4 hydrogens on the left, 4 hydrogens on the right. 2 oxygens plus 2 more oxygens is 4 oxygens. 4 oxygens. 8 cyanide. 4 times 2 is 8 cyanides. Charge on the left is -8, 0, 0, 0. So -8. Charge on the right, this is -4, and this is another -4, -8. Everything is balanced. And look at, now we have hydroxide floating around in there and not hydrogen. This is what makes it basic. Any questions before we try one more? Okay, so I'm going to go Oh, a question popped up. Let's see. Why do we get rid of water? You don't really get rid of it, you just rebalance it. Because if there's 4 on there were technically, so I'll just write it up here. There were 4 waters on the left, and there were 2 waters on the right. And the only reason this happened was because we introduced hydroxide ions. So you just have to rebalance the waters. So all 2 of these end up being gone right here. We're still left with water. It's just 4 minus 2 is only 2 waters. So it's just a rebalancing of the water. You're not actually really getting rid of it. You're just rebalancing it. Does that help? So 4H pluses and 4OH minus is 4HOH. Well, HOH is water. This is H2O. Watch. HOH, which is H2O. This is water. So 4 hydrogens and 4 hydroxides make 4 HOHs, aka 4 waters. Because HOH is water. It's just a different way to write water. Does that help? Yeah, I think that a lot of kids get confused on that. H plus and OH minus make water. So if you have 10 H's and 10 OH's, you have 10 waters. If you have 50 H's and 50 OH's, you have 50 waters. The H and the OH make HOH, aka water, H2O. So hopefully that helps clear that up. We're going to do another one too, so hopefully we can do a little bit more practice. Okay, so this is the last basic one that we're going to do. So we've got NH3 going to N2H4 and ClO minus going to Cl minus. Now I want to talk about something real quick that students have been maybe struggling with, and it came up last class more so. There's no such thing as ClO minus. Meaning, like, to get ClO minus, they probably threw a salt in there. Maybe it was NaClO minus, like sodium hypochlorite, okay? So NaClO minus. And then you end up making NaCl. So where did the NAs go? Well, this is likely a net ionic equation. So the NAs went away. They're spectator ions. So it's not that they're not there, it's just that they're not participating in the reaction. But in order to get ClO minus in there, you'd had to have like NaClO or BAs, or not BA, LiClO or KClO, something else. They're just not including spectator ions in the redox reaction because remember, spectator ions don't participate in the reaction. So what they're kind of showing you is they're kind of saying when you see charges in here, this is like a net ionic reaction, okay? So let's do this. Let's split it into half reactions. Hopefully you can do that by now. You split them into the things that look like, things that have similar elements involved. So let's see. Oh, I'm on the wrong presentation, sorry. So, all right, let's see. NH3 going to N2H2. That's one of my half reactions. Another half reaction is ClO minus going to Cl minus. I'm pretty sure I need to double check that. Yep. Okay. So the first thing you do is you balance all elements that are not hydrogen or oxygen. So in this case, that would be like chlorines and nitrogens. So I have 2 nitrogens over here, so I have to put a 2 over here. The next thing you balance are oxygens. There's no oxygens, so I don't have to balance that. The next thing you have to balance are hydrogens. There are 6 over here and only 2 over here, so I have to add 4 hydrogen ions to this side. Okay, the next thing you balance is charge. This is no charge. This is no charge, but this is plus 4, so I'm going to add 4 electrons over here. Plus 4 minus 4 is 0, and then this is 0. They match. All right, next half reaction. You balance the chlorines first. 1 chlorine, 1 chlorine. Okay, we're good. The next thing you balance are oxygens. There's 1 oxygen over here, so I'm going to add 1 water. That gives me an oxygen. Okay, sorry, I'm trying to do something. Okay, so now I have 2 hydrogens, so I'm gonna do 2 hydrogens. Now I balance charge. This is -1 and nothing, so this is -1 over here. This is -1, but then I have these 2 pluses, so I'm going to add 2 electrons to get rid of those 2 pluses. So -1 and -1, now they match. So both of my half reactions are balanced. Now I need to balance electrons, meaning I need this guy and this guy to match. Well, the easiest way to do that is to multiply this by 2 because that will give me 4 electrons and it will match these 4 electrons over here. So I end up with 4 electrons plus 4 hydrogen ions plus 2 ClO minuses makes 2 Cl minus and 2 H2O. I've distributed that to every single substance in there, and I'm going to get rid of this guy so it doesn't confuse me. Okay. Questions so far? So now look, I was kind of mentioning this earlier in this lecture. Look at this reaction. Electrons are coming out, meaning if this guy's losing electrons. This is my oxidation half reaction. Look at this guy. Electrons are going in to the reaction. So gaining electrons is reduction. So this is my reduction half reaction. Questions about that? Let's talk about why. So I'm going to go into further detail. What's hydrogen? +1. What's nitrogen? -3. What's hydrogen? +1. What's nitrogen here? Let's see, this is +2, so this is -2. Look at it lost an electron, oxidation. Let's look over here. Oxygen's -2. That makes chlorine +2. Well, chlorine right here is -1. So this is going from +2 to -1. So this is getting more negative. It's getting lower, being reduced. This is my reduction half reaction. There are 2 ways to look at it, 2 different options. Okay, so now what do? Now we cancel out everything that's the same or subtract them on opposite sides, and then everything on the same side gets added together. So I have 4 electrons as a reactant and 4 electrons as a product. They cancel. I have 4 hydrogens as a product and 4 hydrogens as a reactant. They cancel. Okay, is that it? Yes. Okay, now this was said it was basic. So what do we do? Oh, let's see, I have a question maybe. Ooh, sorry, is it N2H4? Ooh, did I mess up? Is it N2H4? Sorry, I'm not on the right slide. Okay, look,
Yeah, the original says N2H4.
Okay, I'm sorry. That's my bad. Let me go back and fix some things. Okay, so here's the deal. I'm going to change this. If this is N2H4, I have 6 hydrogens, which really means I only need 2 more hydrogens. This is 6 hydrogens. I only need 2 more hydrogens, so 2 hydrogen ions, which then means I only need 2 electrons, which also means I didn't have to multiply the bottom equation by anything because it already had 2 electrons, if you remember. It was like this. We did this, we added a water, that gave me 2 hydrogen ions, and then I needed the 2 electrons, 2 hydrogen ions, 2 negatives, this is 0, this is -1, this is -1. Sorry. So this is fixed now. So I don't have to multiply by anything, but I still have to cancel. So I have 2 electrons on the left, 2 electrons on the right, 2 hydrogens on the left, 2 hydrogens on the right. Okay, I only have water here. I don't have water anywhere else. So this is it. Now this is the point in a basic equation that you would locate the hydrogen ions and you would add the same number of hydroxide ions. So the question is, are there hydrogen ions floating around in there? Yes or no? They canceled, right? So there's no hydrogen ions left. If there's no hydrogen ions left, you don't need to add hydroxide ions because there's no acid present. So I'm just going to write out what's left. NH3 and ClO minus make N2H4 plus Cl minus plus H2O. And then you go, well, how is this basic then? Like, I don't see hydroxides floating around, and that's kind of confusing, right? Because hydroxides are what our key was to being basic. Does anybody know a substance in here that's a base? This is ammonia. If you did not know, you need to know. Ammonia is a base. Like the ammonia used in cleaner is a base. It is not a strong base, it's a weak base, but it's still a base. So you do have base floating around in there. It's just disguised as ammonia instead of hydroxide. So good job, Andy. You got that right. This is a base. Okay, so this being present is what makes the solution basic. Questions before I move on? Okay, so, all right, disproportionation is a redox reaction where the same species undergoes both oxidation and reduction. It's kind of crazy. So I'm going to give you an example of a disproportionation reaction. Now, I would like you to please balance this by what's called inspection. And by inspection is the exact way you balanced before you ever learned how to balance doing redox. So do it like the old way. If I said, hey, balance this reaction, you would start doing coefficients. Please do it. So you put a 2 here, right? And a 2 here, and it's balanced. So why is this a disproportionation reaction? Well, this guy right here is hydrogen peroxide. Okay, peroxide is this guy in which there are 2 oxygens and each one is -1 to add up to -2 to make this guy right here. Okay, so oxygen is -1 in peroxides. What is it otherwise usually? Well, -2 when it's in a compound. What is it when it's elemental? It's 0. Okay, and hydrogens are +1, hydrogens are +1. So the oxygen is doing 2 things. So the hydrogen peroxide is not only oxidized, it's also reduced. So look for here, it's going from -1 to -2. It's getting smaller. So this is my reduction. From here to here, it's going from -1 to 0. It's getting more positive, meaning it's losing electrons. So that is oxidation. So this species is not only being reduced, it's also being oxidized. By definition, that's what disproportionation is. So I'm going to show you how to balance this the half reaction way. So we'll take our half reactions, H2O2 going to H2O. There's one half reaction. And I'll take my other half reaction, H2O2 still, but this time it's going to O2. And I want you to take a moment and I just would like you to balance these half reactions. So you should be pretty good at this by now. Remember 2 hydrogens, 2 hydrogens, 2 oxygens. So you add oxygen by adding waters. So there's my second oxygen. That gives me 4 hydrogens, and there's already 2 over here, so I only need 2 more hydrogens. Now this side is neutral, so I need to add 2 electrons to cancel out those 2 positives. Now this side is neutral. So this is balanced. Here, so 2 oxygens, 2 oxygens, we're good. 2 hydrogens, we fix hydrogens by adding hydrogen ions. Okay, now we got a balanced charge. So 2 electrons over here, they cancel. This is neutral, this is neutral. Now we reduce 2 electrons, 2 electrons, 2 hydrogens on the right, 2 hydrogens on the left. And look what you have. You have 1, 2 H2O2s. You have an O2, and you have 1, 2 H2Os. So this way you balance by inspection, but it still works out the same way by doing half reactions, because even though this is decomposition, it's also redox. It's a decomposition that is redox because we have a change in oxidation states. How are we doing? Any questions before we move on? Okay, for this reaction, this is an example of a multiple choice question from the AP test. So for this reaction, they have a complete molecular equation. So what I was trying to explain to the last class is that this equation has spectator ions present in it. What they've done is they haven't completely dissociated things yet. So because of that, you're not, you're seeing, I don't know, you're seeing things that you wouldn't normally see in the prior redox reaction. So like, look, most of the redox reactions I gave you had ions in them. Look, there's ions present, there's ions present, there's ions present, aka they've gotten rid of spectator ions. It's not because they're not there, it's just because they're choosing not to write them in the reaction. Now this one does not do that. So what I mean by that is, if I were to break everything apart in here that I could break apart, assuming the substances are aqueous, this would break apart into 6 hydrogen ions, 6 chloride ions, 2 potassium ions, 2 permanganate ions. This is a weak acid, so you would not get to break it apart. Weak acids do not dissociate fully. And then you would do 2 manganese ions and 2 chloride ions and 8 waters. You don't get to break apart, you don't get to break apart water. And you don't get to break apart gases, carbon dioxide, and then 2 potassium ions, and then 2 chloride ions, blah, 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 blah. Question so far? So what they've done is they've not done this. So it's harder to see who's being reduced and who's being oxidized, because this is a complete molecular equation as opposed to like a net ionic equation. So I'm going to get rid of this. I want you to take a moment and practice assigning oxidation states to every single element present in this entire reaction. So I'm going to do formic acid for you. Oxygen is always -2 unless it's in peroxide. Hydrogen is always +1 unless it's with a metal. So by default, you can find carbon. This is +2. This is -2, so that's 0. Minus another 2 is -2. So the carbon right here has to be +2, because all of this needs to add up to 0. All of this needs to add up to 0, 0, 0, 0. So take a second, please, and assign oxidation states. This should be review. This is not new stuff. Assign oxidation states. Hydrogen, +1. Chloride, -1. Potassium, +1. +1. -1. +1. -2. -2. -2. +1. Okay. Are there any questions how I got all of those numbers? So you really want to focus on who's changing oxidation states. The manganese absolutely changes from +7 to +2. And the carbon changes from +2 to +4. So which one is reduction and which one is oxidation? +7 going down to +2 is reduction. Okay, +2 going to +4, so you're obviously losing electrons here. So this is my oxidation. So it says which ones are reduced. Okay, so it's the manganese, which means you technically only have one right option. It's A, because that's the only option where manganese is present. And then let's talk about why it's the 5 electrons. I'm gonna solely focus on the manganese, okay? I'm gonna ignore the potassium and the oxygens just for the sake of understanding it's just the manganese that's changing. It's going from 7 plus to 2 plus. Well, how does it do that? Well, it obviously takes in 5 electrons for it to drop down to 2 plus, which is why it says it's gaining 5 electrons. Are there any questions about this redox multiple choice question? Okay, so last thing for today. This is called an activity series. So on your notes, this is what you should write. This is for single replacement reactions. This is for single replacement reactions. This is for single replacement reactions. And the reason why we're doing this here is because single replacement reactions are redox reactions. They are oxidation reduction reactions. So the whole point of this chart is no, you don't need to memorize it, but you do need to be able to interpret it. The higher up you are, the more reactive of a metal you are. Metals tend to want to lose electrons to become cations. So the easier a substance loses an electron, the more reactive it is. So like lithium is the most reactive metal on the periodic table. And then you go down here and you have like these very unreactive metals, which should make sense to you. They call these guys noble metals, right? Like are noble gases, but they're noble metals. And they're called noble because they tend to be fairly unreactive. This shouldn't shock you, right? Copper, silver, platinum, this is what they make jewelry out of very frequently. It would be kind of unfortunate, right, if these things were super reactive, because you could just be like walking around and like boom, your bracelet blows up on your wrist, and that would kind of be not great. So these tend to be unreactive down here, not very reactive metals. They don't tend to react with much or at all ever sometimes. So this is just a chart to show you the ranking. So now something that we have not done before is talk about a reaction actually just not happening. So in this reaction, if I take a piece of magnesium and I drop it in hydrochloric acid, a reaction will happen. This is single replacement and it's redox. Let's talk about why it's redox. Well, magnesium is 0, hydrogen is +1, chlorine is -1. Magnesium here is +2, chlorine is -1, and this is pure hydrogen, so this is 0. So the magnesium changes oxidation states and the hydrogen changes oxidation states. That's redox. Single replacement reactions are redox reactions, all of them. Now, what you haven't discussed yet is the fact that just because you throw two chemicals together does not mean something has to happen. That is a very big misconception. Putting two things together does not guarantee a reaction. So for example, let's go back to the chart. We were taking magnesium, right, which is right here, and we were trying to kick off hydrogen. And so the question is, well, will it? Well, yeah, magnesium is a way stronger substance, way more reactive than hydrogen. So it's higher up, so it's strong enough to give hydrogen the boot, so that reaction happens. Now, in the next reaction that I present to you, I have copper trying to come in and kick off the hydrogen. So you go back to this chart and you locate copper, and copper is right here, and copper is less reactive than hydrogen. So it is not reactive enough to give hydrogen the boot, meaning if you do this and you drop a piece of copper in hydrobromic acid, literally the piece of copper is going to sink to the bottom and you're going to be bored watching nothing happen. Nothing happens. So again, this is a no reaction. Copper is not reactive enough to come in and give hydrogen the boot. So this doesn't, even though it's single replacement reaction that doesn't work. It doesn't happen. No reaction. Okay. So this just tells you like how, here's the activity series right here on the left under metals, okay? And this tells you how reactive metals are. Like lithium is so reactive that it will react with water. Like can you imagine like having silver do that, right? You're wearing like this like beautiful silver ring and like it starts raining and then the ring like blows up on your hand. That would be awful. So like lithium is so reactive that it reacts with water. And you get down here further and they start to become less and less reactive. So these guys all react with water. But then magnesium or like aluminum, if you take a piece of aluminum foil and you put it in water, nothing's going to happen. Now, if the water's hot enough, it can force the reaction to happen. So that's just exactly what this chart is showing you. And then look, all of these metals react with acids. And then after you have these noble metals down here, they don't react with anything. Not acids, not hot water, not cold water, nothing. They're so unreactive. Okay. So I'm going to switch over to my PowerPoint because this is like, it doesn't do the animation on Pear Deck. So I'm going to switch over to my PowerPoint version of this real quick. Because I have this like animated. So this is everything I just said. This is your activity series right over here. Okay, and then I have a couple of reactions and we're going to decide which of them will react. So we're going to have to do it based on the substances. So this is iron and this is copper. So you go and you locate, and iron is right here and copper is down here. So yes, iron is more reactive than copper, meaning it can come in and kick off the copper and hook up with sulfate. So then the copper's alone. Okay, the copper's alone, and then you make iron 3 sulfate. It could also make iron 2 sulfate. You wouldn't know, right? Iron's a transition metal. You'd have to be told, but this is an example of what it can do. So then the next reaction, we've got nickel and sodium. So nickel's right here, sodium is up here. So nickel is not above sodium. So it's not as reactive. So it isn't even strong enough to come in and kick off sodium. So literally nothing happens. The piece of nickel drops into the bottom of the solution and you stare at it and it doesn't do anything. Okay. How about lithium and zinc carbonate? So you've got lithium up here, the most reactive metal. So yes, it's going to react with pretty much anything. And so it will give zinc the boot and make lithium carbonate, and then zinc will be by itself, single replacement. And also redox. Okay, aluminum and copper chloride, copper 2 chloride. Here's aluminum, here's copper. Yep, aluminum is definitely more reactive. It will switch, you'll get aluminum chloride and copper will come out. Are there any questions on how to interpret the activity series? So I don't need you to memorize it, I just need you to be able to use it to interpret whether a redox or single replacement reaction will occur. Okay, so last thing before we move on. I would like you to take a moment, and I don't need you to predict the products, however, I want you to tell me whether the reaction occurs. Yes or no. That's all I want to know. Does this single replacement reaction happen based on now understanding the activity series? And I'm going to give you 1 minute to figure this out. So it's no, no, no. Look it, here's aluminum, here's sodium. Aluminum is not reactive enough to kick off sodium. So copper and hydrogen. Here's copper, here's hydrogen. Copper is less reactive than hydrogen. It is not strong enough to come in and give hydrogen the boot. Silver and iron. Here's silver, here's iron. Silver is absolutely not reactive enough to give iron the boot. All three of these is no reaction. So this is where I'm going to end today. Let me stop my recording.